the session. It's a pleasure to be here to this very interesting and exciting conference. And thank you for the invitation, for the actual opportunity to present my work. What I'm going to discuss are some possible systematics or hidden signals in the Pantheon plus and SH0ES data. And these are motivated from the Hubble tension. Most of the efforts so far about the Hubble tension has been to try to change the CMB value to another value to be consistent with the SH0ES and with the local value. However, an equally interesting possibility would be to try to lower the value from the local measurements to the value of the CMB. Now, the way that one does it to increase the value of H0 from 67 to 74 kilometers per second per capacity is to actually either change the calibrator, which is change the sound horizon scale at last scattering, or change the shape of H of Z. Now, the change of shape of H of Z, of course, is much more constrained by the data, as we know. So people basically focus on changing the calibrator, the actual sound horizon, as we heard from Vivian this morning. But equally important is to actually think of possibly changing the other calibrator, which is the absolute magnitude supernova. And that's actually the thing that I'm going to discuss today. What are the possible modifications of the analysis? What kind of new degrees of freedom can be introduced to try to see if this absolute magnitude can lead to different values? Now, so let me start with the punchline of all these that I want to make today. The main questions to ask and the answers to with this talk are the following. The first question is the absolute magnitude parameter used for fitting the Pantheon plus data homogeneous? And the answer to this question, as I will discuss later, is the answer is no. The data favor a change of this parameter at about 20 megapascals. Now notice this is the parameter, not necessarily the luminosity of supernova, it's the parameter used in the data. Now a separate question is the absolute luminosity of the supernova derived from the SH0ES data inhomogeneous across the sample? The supernova has basically homogeneous luminosities, absolute luminosities. And the answer, as we will discuss later, is maybe. There are hints for a 2 sigma about change of the actual absolute luminosity at about 20 to 25 megapascals, as I will show today. The next question I will address is the following. Are the Pantheon plus and SH0ES data at various redshift beams consistent with the isotropic Monte Carlo simulations? So if we assume isotropy, we make Monte Carlo simulations, are these data actually consistent with this isotropy? And the answer to this question is also yes, as I will show. And in fact, many bits are more isotropic than the actual Monte Carlo simulations, and this has to do with the fact that perhaps the Pantheon plus uncertainties may be overestimated. And the final question is, are there unexpected changes in the anisotropy among different redshift beams of the Pantheon plus data? And the answer will turn out to be yes. Based on Monte Carlo expectations, there is some unexpected changes in the level of anisotropy among neighboring redshift beams. So this is basically the summary and the results of the talk. So I will now go ahead and try to justify and illustrate these answers in some more detail. First of all, let me review how actually is what is the way to analyze Pantheon plus data. We have 1701 supernova data points, and the SH0ES team have provided these numbers basically, the rexes, the apparent magnitudes, and the distance moduli for the Cepheid host supernovae which live in Cepheid host. And these are 77 supernovae, and this redshift range of the sample is between 0.01 and 2.26. Now, this is from Cepheid supernova and Cepheid hosts. Also, the data provide the difference between the apparent magnitude and the SH0ES number, the SH0ES best fit absolute magnitude. It's a single number, minus 19.245 if I remember well. And this is a separate column in this data. And of course, they have directions, etc. But these are the important numbers that we need for the analysis. Now, the standard maximum likelihood was being used before Pantheon Plus, when the Pantheon, when the old Pantheon data, was to construct this vector Qi, which is MPI minus n minus new model, this is model for the model, for the lambda CDM, for example. This was the covariance matrix. And of course, the new model was corrected to luminosity distance, as we all know. Luminosity is corrected for a flat model to h of z. Lambda CDM is this h of z. And now the important thing is that in this kind of analysis, this log dl of z contains here the logarithm of h0, which is this one here. And this appears degenerate with the absolute magnitude of the supernova, this single number. So it's not possible in the Pantheon data, in the previous Pantheon data, to derive separately the absolute magnitude and the h0 value. So that's why that no previous analysis actually showed the h0 from this Pantheon data. Now the new data includes the 77 Cepheid distance moduli, that is in supernova in hosts with Cepheids, and these are published by the SH0ES team, and they actually have now they have a vector which has two parts. One for supernova which are in Cepheid hosts, and there you can actually write directly this number, which is the distance modulus derived from the Cepheids, not from the model. And then you have also the second part for the rest of the supernova, which include this standard thing. This is the distance modulus from lambda CDM, and you have also again the absolute magnitude. So this now that you see breaks the degeneracy. Actually, this is what they have published in this broad et paper. But notice that they don't have the absolute magnitude anywhere, because this is a parameter which we have done it separate to actually estimate that also. But in any way, these are equivalent. And this is, now we have a broken degeneracy between h0 and n, because here there is no h0 from the new Cepheids. Here there is an h0, so this creates degeneracy. So now this sample can be used to actually derive all three parameters separately: the absolute magnitude, the Hubble parameter, and omega zero matter. And we find doing this exactly the same, almost exactly the same as they found in this Pantheon Plus paper, this prototype paper. But in addition, we find also the distance modulus, the apparent absolute magnitude of the supernova, which was not derived in this initial paper, but the others are very consistent. So we can actually obtain both the absolute magnitude and the Hubble parameter this way. They are going agreement. So the question is, what would happen if we try to include new degrees of freedom in the Pantheon Plus magnitude, and would this actually be favored by the data? So this whole game actually try to test if you can increase. So if you can decrease h0 from the Pantheon Plus data, is to actually introduce new degrees of freedom, as Radoslav showed yesterday, which will be different kinds of degrees of freedom, and see if these degrees of freedom are favored by the data. The data will tell you if these degrees of freedom are useful. You will decrease dramatically chi-squared, and this means that the data want this new degree of freedom. If the degree of freedom doesn't change chi-squared, it's useless, because actually this is the wrong degree of freedom to introduce. So because the absolute magnitude is a very sensitive parameter in the Hubble tension, it's important to see how to play with this parameter and see what happens for the fit of the data. So we introduce two values, one additional parameter, the absolute magnitude at low distances and high distances, at the critical distance, the critical, which is also a parameter here in this fit. And ask the question, this the critical can be connected to this distance modulus mu critical, and when these are equivalent. And then ask yourself the question, what if we now put this parameter, we have to change the likelihood form, and you see we split the upper part, the Cepheid part, into m larger and m smaller and m larger, depending on the distances of the supernova which are in Cepheid hosts. And also we do the same for the other supernova which are not in Cepheid hosts. We split them into two parts, and we do exactly the same thing. We fit with the same covariance matrix, etc. And we ask the question, what is the quality of fit of lambda CDM with the new likelihood? Here we haven't touched anything about cosmology. It's just pure astrophysics at the level of supernova. And of course, the question is, could it be a systematic, or it could be some new physics, whatever, but it's not cosmology. It's astrophysics. Are the best fit M large and N small consistent with each other and with the best fit N of the standard light, in the case where we have a single light standard light? So we thought that what we would see would be that these two are almost identical, and this degree of freedom would not be excited by the Pantheon class. What we saw was this: that the red contours are for the new likelihood, and the blue is for the single M, the old likelihood that is used by Bloch and we found a delta chi-square minus 19. It's huge. And we found a significant tension at the level of these three sigmas, you can see here, between the value of M minus and M plus, and M smaller and M larger. And this is the M omega matter contours, this MH, and you see also actually the H also shifts, but of course it shifts in the direction with Bloch, which shifts towards larger line, but it does shift. So it's not like the omega matter is almost the same, it's not affected very much, almost zero. But H is affected because when you put the new model with the red contours, it shifts within one sigma, or it doesn't shift very much, but it does shift. So this makes you wonder, what if we use a cosmological model or some kind of cosmographic expansion? Would this new likelihood also give different results? For the like it does for H, for example. Now for omega matter we see nothing. Okay, that's clear. Because it's sensitive only to high redshift larger than 0.01. So this is the values of chi-square, and these are the new best fit parameter values. You see the smaller and larger are discrepant at about 3 sigma and more. This 8, the new H, omega 0 matter is almost the same as in the previous model, and this is the D critical, which is about 20 megaparsecs. So something peculiar happened here, even we didn't expect to see this kind of result. So the question is why this happens. Why do we have this, just like put a new parameter and suddenly the data varied so much? Okay, as I said, the omega matter is good. Does this, first of all, the question, does this modeling affect the best fit values of cosmological parameters? That's one question to ask. And the second question is, what's the origin of this tension? Is it systematic, is it new physics, or it's both? So, to understand, after we had some long discussions with Adam, we realized that in fact this is in part at least due to a systematic in the data which has been uncorrected but is well known. And this systematic is called volumetric redshift bias. And I will try to explain this. Imagine that you have an observer here at the center and you have 3 layers, 3 spherical shells essentially around this observer with 3 distances, D smaller, D and D larger. Now these layers of galaxies around the observer have also the cosmological flow, of course, but also they have peculiar velocities. Now there may be some peculiar velocities which are pointing towards the observer, so they shift the redshift inwards to smaller values, or there are some peculiar velocities from the inner shell which shift the redshift upwards to the higher distance. Now, so the delta Z is the non-peculiar velocity of the outer shell, which shift this shell inwards, and also the other shifts the shell outwards. Now the key observation is that the number of galaxies in the outer shell, just by geometry, there are more galaxies. So there are more galaxies projected to smaller distances than from larger to smaller than from smaller to larger because of volume effects. So that's why it's called volumetric redshift bias. There are more galaxies in the outer shell than in the inner shell due to the larger volume of the outer shell. So more galaxies at higher distance are incorrectly projected to lower distance in the Hubble diagram due to peculiar velocities. And so effectively, if you don't correct this effect in the redshift, the redshift effect, you get a smaller value of distance from the model d lambda CDM. So the difference d minus d lambda CDM becomes larger than 0 instead of 0, as one would expect when you fit a cosmological model. But this is a pure effect of volumetric redshift bias. And that's important for redshift small, less than 0.01, because that's where the peculiar velocities are important and can induce this problem. Now, this is the origin of what we saw yesterday in Diagon Brute's talk, where we saw that this difference of the distance moduli, mu observed minus mu model, is okay, it's very close to 0 for most rates, but suddenly it goes up in rates less than 0.01, and you have this. But this is important because it tells you that you cannot use a single absolute magnitude in fitting the data, because simply the data themselves, unless you correct for it, tell you that the M is not constant. So the way to see it, therefore, for z less than 0.01, we have that this difference is when you, because of the volumetric redshift bias, is larger than 0, while if you had used the correct distance modeling for the models, correcting the redshifts, it should be 0. Now, if we incorrectly assume that the distance modulus of the volumetric redshift bias and the true are equal, then we actually get from this equation that m smaller is smaller than m larger. That is the value of the absolute magnitude for larger distances. So the volumetric bias is not, if it's not corrected, then it leads to a lower supernova absolute magnitude and less than 0.01. So also if you don't correct it and you try to put cosmological parameters there, and you demand that this is 0, then you will get incorrect values for the cosmological parameters in principle, at least for this part of the Hubble diagram. But because they have put very huge errors here, this is not really an important effect because they have essentially neutralized this data when it comes to cosmology compared to the other data which have less error bars. Now, for 0.01, there is no such an effect, so we'll get the normal equation with no problem. So with m larger. Thus, we do expect m larger smaller than m smaller, larger than m smaller. And the question is this the only reason for this effect that we found? 5 minutes? 4 minutes? Huh? Okay. So anyway, then we use another likelihood for z less than 0.01 where we eliminate these points, but then we see again that this effect is still there, but it's much smaller. If we eliminate these parts, so there may be also some physical reason for this, even though much less significant statistically, because the effect remains even after we take away all the Hubble diagram points with z less than 0.01. And these are the corresponding. So now we go back to the SH0ES data, which are the actual absolute magnitude directly measured with the SH0ES. So we take this 37 hosts, 42 actual supernovae, 37 hosts, and you can actually plot them in terms of distance. And you see that in fact, even by naked eye, you can see that these supernovae here have a smaller, have lower absolute magnitude, which are low distance, than the rest of them. In fact, in this region also a similar effect appears, but at least those seems to be the case. And the question is how often would this happen by chance? So we ran a Monte Carlo simulation. We calculated this, we split in two parts, larger distances, smaller distances, and we calculate the difference between the mean m larger and mean m smaller divided by the error bars. This is the sigma. We can select. In the real data, sigma max was found to be 2.75 at the critical, about 82.4 megapascal. This is for the SH0ES data, not the Pantheon, not the full Pantheon now. And the question is, how often would this happen in Monte Carlo? How often would we have such a big this inhomogeneity? And we find that about 7% of the data of the Monte Carlo have a similar kind of effect, so it's about a 2 sigma effect. About 94 of the data have this kind of property of having bigger sigma max, equal or bigger than the real data. So it's not very statistically significant, but it is something to keep in mind. Now, then we try to, in a more recent paper which appeared a few days ago, I tried to look at the anisotropy. Yes. So before I had looked at we had looked at the homogeneity of the absolute magnitudes. Here we looked at the isotropy. So here you see the standardized absolute magnitude of supernova obtained using this definition as the CDD of the sky. And then we can actually split them in various redshift bins, trying to see what will be the anisotropy level at various redshift bins. So we have, for a random direction, we have the absolute magnitude, the mean absolute magnitude in the north and in the south. We compare them through this sigma parameter, which measures the anisotropy level for various directions, various random directions, and find the direction of maximum anisotropy, as usually in this method. And repeat this for n isotropic Monte Carlo samples to find the anticipated range in the Monte Carlo, in the isotropic case. So we compare the real data sigma max, as before, with the Monte Carlo expectations. And here, this is the result. You see, these are the Monte Carlo data, and these are the real data. You see that they have less sigma max actually than the Monte Carlo. This is probably due to the increased uncertainties of the data compared to the dispersion. And you see that also there is a jump in the anisotropy from this redshift bin between 0.01 and 0.05 to the next redshift, about 20 megaparsec is this, 20 to 30 megaparsec is this redshift bin, and then it drops again. So we have a peculiar kind of jump in the anisotropy level, which may be of interest. Now, the question is, how frequent are those in the Monte Carlo isotropic data? How frequently would this change occur in the Monte Carlo data? And we see here this about 2 sigma level. One isotropy. How much time I have? 1 minute. Okay. And we do the same with the SH0ES data. This is a cumulative distance being in this case. We compare again with this is the sigma max for the Monte Carlo, the blue ones, and these are for the real data. You see a sudden change happening also here. And you ask again what will happen in the Monte Carlo data. It's about 2% of the Monte Carlo data have a similar or bigger change of anisotropy level. So a possible physical realization of this effect could be in the following physical situation. Imagine that you have a bubble of different physics at some range, let's say about 30 to 40 megaparsecs, and you have an off-center observer here. This observer will detect inside the bubble, it doesn't touch the borders of the outside of the main physical bubble, we'll see isotropy. Once, however, it goes to a bin which is between this bin and once it touches the real external bubble, one would see a sharp increase in isotropy, and then once it goes beyond a bin beyond that, you again see back to isotropy. So, in some mechanism, this could actually be somehow qualitatively anticipated on the basis of this off-center observer. Okay, that's all. Thank you very much for your attention.
Thank you very much. Any questions? Yeah. So this is related to the discussion yesterday about whether or not this is statistical fluctuation in a small sample. So it's a dipole at the absolute magnitude, right? That's what they're tracking.
So I think about the second part about the isotropy now.
Yeah, isotropy, right? And so, yeah, Adam Rees says that's a statistical fluctuation. You said the chance of that is maybe 2%. Is that what you're saying?
Well, I'm saying in the SH0ES sample, it's about 2%. Again, this is a cumulative bin, so we start increasing the size of the bin from inside towards outside, and suddenly when we reach something like 30 or 40 megaparsecs, suddenly the anisotropy level drops and becomes constant until we go out to about 70, 80 megaparsecs, which is the sample of SH0ES. Now, for the other sample, for the Pantheon Plus, it's less significant, 7%. It's about 2 sigma. But these are in bins. You see, because we have more data in the Pantheon Plus, we can use bins. Here we use cumulative bin because we have a small number of data. We don't want to completely destroy statistics. So for SH0ES, we have cumulative bins. This is T max here. But for the SH0ES, this is a bin. See, this is a range of redshifts here, of about equal number of data points. So anyway, that's what we find. Maybe one can actually argue here. The Monte Carlo says this. We keep on to make a Monte Carlo also. If you don't make a Monte Carlo, whatever you find here is useless. So we made the Monte Carlo to see how often would this happen in Monte Carlo, and we find here in Monte Carlo that happens 7% of the sample. That's the, of course, if you're going to stay beyond the Monte Carlo, you cannot really stay with relevance.
So one of these anti-positive issues, right?
One, this is Pantheon Plus, the full Pantheon Plus data, the other is just the SH0ES data. Taken from the SH0ES paper, not from the Pantheon Plus, because they're not exactly the same, as I have told you.
Any other questions or comments? Yeah?
Can you try to check the axis of this anisotropy is aligned with
Yeah, we've checked it. It's not relevant. It's not aligned. So this is not a velocity effect. This effect has to do with the intrinsic properties of supernovae. So even though the dipole, if I try to find the dipole of the Pantheon class, it may be aligned, but this has to do with redshifts and velocities. This is not has nothing to do with velocities. It's pure intrinsic properties of supernova. So we would be very surprised if it was aligned with the CMP, but also we find that it's not. In fact, in the paper we have evaluate the angles in various redshift bins.
I'm thinking about another alignment, because as they correct for particular velocities, there is also this dipole component, which accounts for any kind of mass that is not counted in the local.
You mean because of the low mass relevance? Okay.
And there is a kind of approximation that this dipole component correction, it works in every place in the local volume, which is roughly 100 megaparsec. So this is like kind of zero other approximation, yes. If there are any variations for any reason, yes, then it can kind of introduce scale dependent, isotropy.
No, that's true. I mean, this is we have not found any clear, at least because there are a small number of bins here. There's no clear correlation between the redshift bin among the distances and the various redshift bins. But also again, these are independent bins. So in this picture that I showed here, if it can be discussed in this fashion, you don't expect very big correlation between the bins because if one bin is probing the different physics problem, then that should be correlated with the outside.
So, I have a question about the correlation where you show the correlation between absolute and numerical Hubble parameter, H0.
Yes, well, that is in the beginning, In the beginning, here?
New decrease of
You mean, anyway, this,
yes.
here? Here? Here?
Okay, so where we see that for m less than the mu critical, the constraints are better for m less than critical on H.
On H, very different, yes.
Yeah, but I expect that the H value we are getting is having lower constraints, and that we are getting from m less than the critical distance. But it should be other way around, because for after the mu critical, that's where the Hubble flow or the last distance starts, and there you calculate the H0.
Yes,
From the mu less than mu critical.
If you take out the level that you critical out, because they favor a smaller, they favor lower, then you allow the other part, which is mostly dominant, to increase further the H bar. Because here you see this part, this upper red part, okay, here corresponds to the T larger than the critical. Now this is free now from this heavy part we have removed it from there. So it's like allowing to see this M larger is going to becomes larger. So if this becomes larger, then this means that also H also increases. Because these are degenerate because of this relation here. What is it? Because of this relation here, you have M and H not being degenerate. Okay? So if you make this in one direction, this is 1 over H naught, okay? So if you increase this, you also increase this. Because it's mine.
I was talking about the constraints, not the values.
The
constraining power.
The constraining power, you see that you're saying the constraining power is about the same. It doesn't change very much. Well, it becomes a bit larger, if I remember. Okay, you see the red part, because it has somewhat smaller number of points, it's a little bit larger. If you see this red part here, it's a little bit larger than the blue part.
On the H parameter.
And also on the H, because you cannot see it clearly on the H, but you can see it clearly here. The upper part is slightly, but also the value of H has changed. You see the best value has increased. Because if you increase M, you also increase H.
Maybe we can continue this in the coffee break. Yeah. So let's thank the speaker again.